Hello again, welcome back to our computer vision series. The last time we have looked at the Xavier Glorot original paper. We're talking about activation functions and how they affect the actual training of the model. We talked about sigmoid activation and the saturation and the stifling of the gradients. We talked about parameter initialization and how that affects training. Today, I just want to reiterate on the same in a more practical fashion, and also to introduce you to a new tool called Tensorboard. So we start with the similar code that we had before to load the dataset and train the model. This time, I'm going for fashion MNIST dataset, which is slightly harder than digits because I think we pretty much solved digits already. I just do the imports, load the dataset. The code is similar to the previous one, and here is how images in the dataset actually look like. So this dataset is about classifying clothes. So it has low resolution items of clothing that look something like this. And the model is pretty much similar. So we have a couple of convolutions. We have max pooling. And then on top of that, we have linear layers. And so the actual forward pass sort of applies convolution, then activation function, then pooling, then again convolution, activation, pooling, and then flattens it out, and then dense layer, and then the output. So this is exactly the same as we had before. So the last time, the only sort of visibility that we had, here it is, by the way, was sort of printed out to our Jupyter notebook, which is, I guess it's okay to begin with, but then it's obviously not so convenient. So one problem is that, just the amount of text is getting pretty long. Then again, if I want to experiment on the model, if I want to train another one, I will, as soon as I restart this cell, it will sort of lose all the text that I had before. So I don't really remember what happened last time. And finally, I might want more information, like we've seen in the paper with the actual gradients and actual values of activations. So this is where Tensorboard comes in handy. So to use that, I actually import it. I initialize what is called a writer. So a writer is basically an object that you call to add some information to it. Let's move a bit further. The next modification I did is here, right? So I have my training loop. It receives epoch because I need to report that to the Tensorboard, and this same writer that I created before. And then I just want to report training and test loss at the moment. So I already had the loss when I computed it here. So I'm going to report it once every 100 batches, the same way we did to the sort of Jupyter console. And I just sort of pass that to the writer. So I call writer.addScalar. I call this signal training loss, pass the actual loss, and I also pass in the step. So basically, as we'll see later, the Tensorboard will sort of track time when you had pushed the signal and the training step that the model was doing at that moment. So this allows you to sort of track the training from the beginning to the end. And I do pretty much the same when I do the testing, so evaluation on the test dataset. So again, I pass in the writer, I pass in the epoch, I compute the current step based on the epoch and the total length of the test dataset. And then I report the loss and the accuracy. And now we start training. Right, so the training has started. It should work now. So I'm going to the console. And somewhere here, when I initialized the writer, I said that we should put all the actual data to this directory, so runs/sigmoid1. And it's important to sort of name your runs somehow, because we are going to look at a few different configurations for the model. And I don't want to confuse them. So I call this one sigmoid because I'm using sigmoid activation function. So now I'm going to the console. And in the runs directory, what I can see is that indeed I have a subfolder named sigmoid1. Let's see what's in there. And it contains some data that I suppose should have all of these signals. So now I'm going to launch the actual Tensorboard. So Tensorboard is the command line tool. It's available on Mac, it's available on Linux, on Windows too, I suppose. So I'm going to put in the description the sort of instructions on how to actually install it. So I launched this. It will take a bit of time. No rush here. Let's look how our training is going. So yeah, since we are using activation of sigmoid, it's taking quite a long time for the model to actually pick up. Let's see how long it actually takes. Let's see who will be first, the Tensorboard or the model. Okay, Tensorboard is here. Right, so this is how it looks like. It's basically a web UI. In here I can go to the scalars tab, and here it sort of shows me what is happening, right? So here I have my training loss that is slightly going down, but not really picking up the pace. I have my test loss. I have my test accuracy. Good thing about it is that, you know, the training is still going, right? And I can just press this refresh button, and it sort of catches up on all the recent changes that were happening here. And this is basically the graph of the signal that I put here. So exactly the same as I reported it to the writer, plotted against the step here. But I can also sort of change that to plot against the actual time, which might be useful if you sort of track the speed of training, for example. Yeah, and also have relative time. Right. So let's wait a bit until it is trained. All right, we are here. So the training has completed to train for 200 epochs. We can see that it still doesn't pick up the training, you know, accuracy is still stuck at 10%. This is what happens in Tensorboard. So accuracy is just stuck here. Test loss went down a little bit, but not much progress there. Well, this is sigmoid. You know, our architecture is slightly different from the paper. So we have some convolutions. And in the paper, they just consider the linear layers. So maybe that's why, you know, it's not picking up. Either way, you know, we knew that sigmoid is going to be bad. Now let's try to look at hyperbolic tangent. So the first thing I do is to change the folder name for Tensorboard to sort of make sure we don't make a mess of it. We'll not lose the data, but saving something with the wrong name is going to be tricky, you know, to understand what's going on afterwards. So the only thing I'm changing is the activation function. Everywhere I'm using hyperbolic tangent. And so I'm just running all of it, and let's see how it goes. So the running has started. Training is going. We should wait a little bit until Tensorboard catches up as well. We can instantly see that accuracy is already going up. So it's at 50% now. With sigmoid, it was stuck at 10% for like 200 epochs. And here we are already at 54 on epoch number 4. It's still not picking it up. Let's wait a bit more. Right, and here it is. Right, so we can see that we have 2 runs now. So the orange one is the sigmoid, the blue one is the hyperbolic tangent activation. It instantly sort of jumped up with the accuracy, so it's already giving us good results. Test loss is going down, training loss is going down, so it is looking good. And this is like, this sort of Tensorboard is the classical setup. So at the very least, if you are training a model, you would want to plot test accuracy and train loss to sort of understand what is going on with the model, to compare the speed with which the model trains as compared to other runs, for example. Another good thing about Tensorboard is that the actual data is saved on disk in the runs folder. So, you know, if something happens to your code, if the code catches an exception and just quits, you know, you'll still have the data, you'd still have the accuracy, you'd still understand to debug what's happened before. So it's sort of persistent in a sense. And it lets you compare different launches, which is really useful. So now let's just wait until the hyperbolic tangent trains properly as well. There we go. Hyperbolic tangent is trained for 200 epochs. We can see from the look of this plot that it's not quite saturated yet in terms of training. So, you know, it's taking a long time. You should probably train it a bit more if you want better accuracy, but this is not what the current video is about. So now, let's try to understand what actually happened here with the sigmoid. And to do that, I want to plot more metrics, right? So, in the paper, in the Xavier paper, they were plotting the values for the actual activations. So whatever it is that goes out from the activation function, and the actual gradients. So let's do that. This is the network that we were training, right? So doing forward pass, which is basically save each step to the X variable, right, and just return that. Now to plot the activations, we would need to save that to intermediate variables. So I'm going to do that. So we need the output of the activation. So let's just save it to a different variable. So this is going to be Act 1. This is going to be Act 2. This is going to be Act 3. And this is going to be Act 4. And then final X is the output. And we return all 4 of these. So basically I have 2 convolutions and 3 linear layers. Last layer just outputting the actual output of the model. So I'm going to return output as well as these 4 intermediate activations. Let's see if it actually works. No, it doesn't. Yeah, because that is supposed to be Act 4. Right. So now it works. So during the forward pass, I return intermediate activations as well as the actual output of the model. Now I just need to modify the training and test loop. So instead of 1 tensor, I now get 5 of them. And yeah, all of these are the tensors, right? So I can just say that, yeah, prediction, activation 1, activation 2, activation 3, activation 4 are the results of calling the model. And so activation 1 is tensor, right? And we can see the shape of it, right? So the first dimension is the batch size, and the actual output of this layer after the activation function has the dimensions of 6 times 24 times 24. So if you recall, we started out with the 28 by 28 images. After the first convolution, it shrank down a little bit to 24 by 24, but we have 6 channels instead. And this is what the first activation is giving us. Now I need to come up with a way to sort of average that out to just one number in a meaningful sense, right? So obviously I can just plot the mean, right? So let's just do that first. And I'm going to do that for these intermediate activations only once in 100 batches. So this is going to be act 1 mean. Actually, let's just write a separate function for that because we're going to use that at least a few times. So I'm going to receive a tensor and a writer and the step, and this is what I'm going to do, and the name as well, right? Writer step, right? Name. So this is going to be name mean, t.mean. Good thing about tensors is that I can just call some of the statistics directly on them. So I don't have to write the code for calculating the mean from scratch. So dot mean means mean, average. Dot std means standard deviation. std. Then what else do I need? Let's go for 98th percentile. This is like not exactly the maximum, but something that is really close to the maximum. So the point that sort of encompasses 98% of all the values. And this sounds like enough, right? So I have mean, standard deviation, P98. So let's go for this. And obviously I'm going to do that for activation 1. So I'm passing in activation, writer, step, and the name being activation 1, activation 2, activation 3, activation 4, 2, 3, 4. So this code is not ideal. I'm just sort of writing out all the 4 activations by hand. Luckily, I have a rather small model. Otherwise, I would have to, write a lot of code. So I could probably come up with a better way of doing that in a loop or something like that. But for now, this will work just for demonstration purposes. And this sort of handles the forward pass when we actually call the model and get the prediction. I also want to plot what is happening to the gradients. And we can get the actual gradient by just, we can get the model, right? So this is the model. It actually has all the convolutions and linear layers saved as part of the model. I can access specific layer, but by using just dot notation. So model.conv1 returns me the actual layer, and dot weight actually returns the weight of this convolution. So this one is 6 by 5 by 5. And if I call dot gradient, this was supposed to return me the gradients, right? But right now it is returning none because I'm not in the sort of optimization loop at the moment. I called 0 grad the last time I called it, and now I don't have the loss. I don't have the gradient computed for anything. So to fix that, let's just run training loop by hand. So I have threads, I have the tensor, so I can go through this, and this should work, hopefully. Right, let's copy that to device as well. To device. Okay, this seemed to work. So now I should be able to access model.conv1.weight.gradient. And there it is. This is the actual gradient. So again, I can sort of do the reporting once every 100th batch during training for this gradient, right? Let's call this grad1, model.conv1. Actually, let's call this .conv1 grad so that we know where it comes from. I can do the same for convolution 2. And then there's 3 layers, FC1, FC2, FC3. FC1, FC2, FC3. Right, so now this should work. I'm not doing anything during the test run. So now, yeah, right now I have previous model loaded. Oh yeah, still have one problem here because I have modified what the model is giving us, but I have not modified the test loop. Let's try it right now. Still no. Report. I had it somewhere here, didn't I? Report tensor. Let's just call that report. Now it should work. So yeah, this is just to make sure that what we have actually written works. But now I had some model pre-trained to some level. Also forgot to rename my launch. This is not good. So I'm going to interrupt it. I'm going to rename my launch to hyperbolic tangent 2 and just run all of it from scratch. And we'll see how it goes in a little bit. And no, we don't. I have some problems here. Interesting. Maybe it has to do with the way I pass information to this function. Oh yeah, so the problem here is that I'm doing the reporting after calling 0grad. So let's move the stuff around a little bit. Now it should work. And it is working. The training has started. I am using hyperbolic tangent here as an activation function, so the accuracy is quite rapidly going up. We can also see what happened to the previous launch because I sort of started it 2 times. Let's check out what was happening in test accuracy, right? So, and now I just have two plots, and it looks a bit weird, but thankfully they are actually saved on disk as separate files. So I can just delete the previous file if I want to sort of resurrect this launch. I can delete the file that was accidental, relaunch the entire Tensorboard, and it will work fine. But let's come back to what we were planning to plot, right? Because the training has already started, right? We can compare this new hyperbolic tangent to sigmoid on the test accuracy, and test accuracy is quite rapidly going up. And then let's see if everything else makes sense, right? So this is the first activation after the first convolution. And you can see that the mean is 0.14. We might actually expect it to be close to 0, simply because this is the hyperbolic tangent. I have it somewhere here, right? So it should be symmetric. So we might expect the mean to be somewhere near 0, and the actual values to be somewhere closer to the tails. And so standard deviation, there it is showing us 0.44. Again, this might be hard to interpret because at least we know that it's not all stuck at 0. It has some sort of noise. So that might mean that some values are somewhere here in the upper tail, and then some values are somewhere here in the lower tail. And then after averaging out, you get the mean that is close to 0. And then P98 sort of shows that at least some of the values are actually becoming saturated here. So our tangent is sort of getting saturated, at least in some coordinates. And I'm pretty sure something similar is happening to other activations. Now, how about the gradients? Well, it's a little bit harder to understand what's going on here, sort of without comparing to activation functions. At least we see that, something non-trivial is being reported here. So what I'm going to do is just wait until the hyperbolic tangent has trained successfully, then relaunch the training with all the activation and gradient reporting for sigmoid, so that we can actually understand why it got stuck at 10%. And then we can sort of make some conclusions. And here we are. So I have trained the hyperbolic tangent for 200 epochs, as well as the sigmoid. So I repeated the training for sigmoid. It's still stuck at 10%, but now I get to see what's actually happening with the activations and gradients. So let's start with the activations of the last layer. And quite surprisingly, it is not saturated. It is not at 0. So I can look at P98, standard deviation. So standard deviation is quite small. And then the mean is somewhere around 0.5. So just to remind you, this is here. So this is not the saturated mode. However, it's still a problem because, it's above 0. And we actually want the mean of the activation to be somewhere around 0. Otherwise, if you have this huge matrix of parameters, so in our case, it's what, let me check. So the final matrix is going to be 84 times 10, right? So if you have this 84 numbers, each of them are significantly above 0, roughly 0.5 in our case. And you multiply it by this 84 by 10 matrix. Basically, every coordinate in the output will probably be huge, right? So if you multiply by like a matrix with 1 for each weight, it will be like 1 times the first coordinate plus 1 times the second coordinate and so on. So it's going to be inflated by 84 times. Now this is not what happens here, because obviously these parameters are being trained, and they don't want to sort of inflate the prediction to infinity. But instead, what probably happens is that to sort of keep the overall prediction after this matrix multiplication sort of under control, they pretty much, the weights end up being in such a way as to pretty much zero out this prediction, which causes gradient to be really small. So now let's look at the gradient. So starting with P98 for the last layer. The blue one is the sigmoid. It looks more or less okay, right? So the final layer is doing good. But then the layer before that, we can see some difference already. So now sigmoid is somewhere of an order of magnitude below the hyperbolic tangent. Then for the first linear layer, it's way below. It's somewhere around 0. And then if we look at the gradients for convolutions, it's even worse, right? So having this sort of above 0 mean of activations caused the sort of, during the backprop, the gradient to sort of become smaller and smaller. So now, it's not even moving anywhere, right? It's not even becoming saturated because it's stuck so hard that it's not even moving. So this is what happens. Again, don't use sigmoid, but it's a nice demonstration of the sort of things you can observe with just a little bit of code and Tensorboard. So luckily, PyTorch already has all the complexity handled in terms of how you can get the gradients, how you can plot the gradients, the numerical stability of it, and so on. Let's say this is it with the sigmoid. And what I'm also going to do is check out the other activation function that we haven't looked at before, the soft sign. Soft sign, right? So I'm running this. And just a reminder, the soft sign looks really a lot like hyperbolic tangent. So hyperbolic tangent did quite good in our training right now. And then soft sign is similar. It is symmetric, but then the asymptotics of approaching the saturation are completely different. So it is supposed to approach slower, which hopefully will cause the gradients to be bigger and training to be better, but I don't know. Let's see. So yeah, it is training. Let's wait for it to train for a little bit. It should be trained now. So I'm refreshing my Tensorboard. And again, first I take a look at the actual accuracy. So here I have hyperbolic tangent, which is red, and then soft sign, which is pinkish. And yeah, unfortunately, soft sign is sort of under the can H, so it's always sort of behind in terms of accuracy, and it doesn't seem to be able to overtake it. We expected that soft sign will saturate less. That will cause the gradients flowing backwards to be higher. Now, if we see at the actual saturation values, right? So this is for the last activation, and so P98 for hyperbolic tangent is 0.92. So yeah, here it is. So it's not completely saturated, and again, this is just P98, but it is sort of going there. And then soft sign is much less saturated, so we should expect gradients to be higher. But if we look at the actual gradients, so the mean is around 0, and looking at P98, it is still sort of worse, slightly worse for soft sign than it is for hyperbolic tangent. So apparently, at least in our case, this logic behind saturation in the gradients does not work exactly as we expected it to, but still, nice to try. And yeah, sort of looking at the actual loss or the accuracy is the first thing to do when we do the experiments, because, here soft sign is sort of losing, so we know that it's not a good activation function to begin with, and only then can we look at gradients and activations to actually understand what's going on. And now, as the final step, it's still training, so I'm just going to interrupt it. As the final step, I want to add proper initialization. So let's go back to our model. So right now, everything is sort of default initialized. And default in PyTorch is uniform with the square root of input parameters bounds. So it is asymptotically correct. So it is at least sort of taking the square root of input parameters at least helps you make sure that your predictions from activations from layer to layer do not sort of inflate too much. But then that was shown because vanishing gradient when going backwards, because it sort of doesn't take into account the sort of backwards prop where the sum will be taken from the size of the output, not the size of the input. And so if the thing is stable during forward prop, and it will be stable because we are training it that way, right? Even if, the parameters actually become really high, the network has to output some bounded number. So it will sort of adjust the parameters to make it stable across the layers. But the gradients will vanish, right, because of this. So to add proper initializations, I call pytorch.nn.init.xavieruniform. So let me just take a look at the help for this one. So it takes the tender and then an optional gain, which we haven't discussed yet. So let's just stop with the tender like this. Right, so this one worked. So as you recall, the sort of Xavier uniform initialization looks into the number of inputs for the layer and the number of outputs, and sort of computes this average, this sort of compromise between forward path and backward path to sort of prevent gradients from vanishing. But since in PyTorch, when we initialize a layer, we provide the number of inputs and the number of outputs, we can just pass that tender to the initialization function, and it will know what's the input, what's the output, and it will be able to initialize everything correctly. So we repeat that for the second convolution, for FC1, FC2, FC3. Just running it once again to make sure it works. And now, oops, still got to change the activation function and the name of the run. So since hyperbolic tangent was the best, I'm just going to leave it as hyperbolic tangent, and I'm going to call it tan-h Xavier to sort of underscore that we are using Xavier initialization everywhere. Right, so I'm just going to run it all. And here we are. The training for Xavier initialized hyperbolic tangent is done. So in here, we can see results for all the launches so far. This is the test accuracy. I'm just going to disable sigmoid and soft sign because they weren't any good anyway. And we can see that from the first epoch, the Xavier initialization is already much better than the default one. And this seemed to continue along the training. And even here towards the end of the training, we still see some benefit from it. We can try to zoom in here a little bit and see that indeed this green one is the Xavier initialized, and it's still sort of a little bit above the default initialized one. So it is giving us gains. That's good. Now we can try to see why. So if I look at the gradient for convolution 1, for example, which is the sort of the deepest layer in this network. So red one here again is the default initialized hyperbolic tangent, and the green one is the Xavier initialized. And in the beginning, the gradient for the green one is okay, and then for the red one, it is almost zero. So because of the incorrect initialization, the neural network had really tough time sort of starting out, which is what you see in this accuracy plot here. It takes much longer to train initially, and then they almost converge because after some time has passed, the potential effects of initialization sort of degrade a little bit. But still, we, at least for the 100 epochs that we trained the model for, we can still see that initialization actually improved the benchmark a little bit. Now, I also want to talk about the rectified linear unit activation. This is the one we used in our previous practical examples, and this is probably the most popular in computer vision. So this is how it looks like, and the motivation behind rectified linear unit is to sort of combat this problem of saturated activations. So we've definitely seen that with sigmoid. We might also sort of observe that with hyperbolic tangent. As it approaches the plateau, as it gets saturated in the right tail or the left tail, the gradient goes to zero as well, which might stifle the training. And to combat that, people come up with the rectified linear unit activation. So it's actually much simpler, right? This is basically the max of input and zero, so it's easy to compute. It's also not strictly differentiable here at zero, but people sort of tend to ignore that, or just say that, it might be smooth right around the zero and then it should work. It does not saturate, so it just goes on and on as a linear function to infinity, meaning that the gradient in the right part of the activation function is just always constant, which is supposed to be good. And then the actual nonlinearity is achieved somewhere around zero. So in some cases, neurons will not be activated, so the output will just be zero. And in some cases, they will be activated. So this sort of allows the function to, allows the network to learn nonlinear functions as well. And potentially that might have some problems as well. So one potential problem is that if all the neurons are sort of activated, if all the neurons are always in this linear regime to the right, then it's just always linear. And the neural network loses expressivity and will not be able to approximate nonlinear functions. Another potential problem is that if neurons are always not activated on all the inputs, they just get stuck there, because on the left part of the activation, the gradient is zero, so nothing is changing. If that is the case for all input pictures, then this particular neuron is just stuck there. So it can happen with the rectified linear unit activations that parts of the network are just dead and they will never sort of activate again. So let's try using this activation function, and let's also add some code to actually explicitly track these two things. So first one is just how nonlinear it is, which is just the average number of zeros in the activations. And the second one is how many completely dead neurons we have. I'm going to start with just renaming the folder to not confuse myself again. Then I'm changing the activation function in the network. I'm quickly running it to see if it actually works, and it does. So now I want to rewrite the reporting function a little bit. So let me grab my tensor example. So this is one of the activations I had saved before of the first dense layer. So it's a tensor of 64 by 120. So 64 is the batch dimension, so it receives 64 input images. And then 120 is the sort of output size of this layer. So how do we get the average number of zeros here? In PyTorch, it's pretty easy. So we get zeros by just comparing the tensor to 0. This turns this tensor into a similar dimensionality tensor of Boolean values, false and true. And to calculate average of that, I need to convert that back to float, turning that into ones and zeros, and then just getting the mean. So for this activation, I have 55% of 0 coordinates. So let me just copy that to my reporting function. Right, so I'm going to call that negative ratio, and then copying this here. Right, now to calculate the number of dead neurons, I will need something else. So this one is just number of zeros in the entire tensor, but I can also take the mean along a specified dimension to get the sort of average across that dimension only. So if I now write dim equals 0 here, instead of sort of averaging out everything, it will average out over the first dimension only. So let me save it somewhere and just show the shape of that. So now this has a shape of 120. So basically I got an average across my neurons, sort of collapsing all the input pictures into one number, but I still get individual numbers for each individual neuron, which is what I want. Now, a neuron is dead if it outputs 0 on all the input images. So now I want to compare this to 0. And again, I'm turning that back to float and calculating the mean. So this tensor has 25% of dead neurons. And again, let me just copy that here to my reporting function. And I'll just call this dead neurons. Right. Now this should work. So let me sort of restart the entire training, and we'll see how it goes. And the training is done. Let me just refresh the data. Right, so first I look at the accuracy, and I can sort of see that the rectified linear unit, the ReLU, is losing. So it started out slightly below the hyperbolic tangent, and towards the end of the training it is still sort of a little bit behind. Unfortunately, I was really hoping it will do better. Now let's check out the actual gradients, starting from the top layer. So again, the mean of the gradient should be around 0, but then P98 sort of shows how big it can be. And here we can see that the gradient is actually much better, even for the last layer. And then the layer before that is also better, and the layer before. So it did help with the size of the gradient, but then final result is still worse for some reason. So there's clearly something here that we don't completely understand. Now let's look at the number of dead neurons. So this is just an approximation because we are looking just at one batch And still it's not too bad, right? So it's around 10%. So at least most of our network is alive and well for the last activation. And then the negative ratio is 0.4. So everything seems to be fine with nonlinearity. Same goes for the layer before that. Dead neurons is also fine. So the overall health of this activation function looks good. A final result is not so good, unfortunately, but it is what it is. Maybe something will be different with more complex, deeper networks. Now, one last thing I wanted to show is the optimizer. So right now we sort of started out with the stochastic gradient descent, which was sort of advertised on the PyTorch website, in a sense. Now, let me just sort of show how it actually looked like with Adam, which is considered the industry default. So whenever you don't know what optimizer to use, just start with Adam. So I'm still going to train rectified linear unit, and I'm just restarting the whole thing. And here we are again. This time it was much faster. So here we have the accuracy for our newest launch, and the orange one is the rectified linear unit with Adam optimizer. And we can see that it sort of started out much higher than all the competitors. So it managed to beat all the launches before that in much fewer number of steps. And also, if we sort of zoom in here, we can see that the highest point, which was somewhere here where we should have stopped, is also sort of higher than for SGD optimizer even after all the training was done. So it took maybe 100 epochs less, and it converged to a better optimum, which is just sort of showing what else can there be and how important an optimizer can be. So we are going to have a video about optimizers next. And to sum up what happened today, so we have looked again at the results of the Xavier original paper. We have looked at the activation functions, at their saturation, at the sigmoid activation. We have looked at parameter initialization and how that can affect training. We implemented all those metrics in practice using Tensorboard. And we also tried rectified linear unit and Adam optimizer. So stay tuned for the next one. See you soon.